Good morning. So I want to look at, today we're going to be finishing up our discussions of chapter 10. So a little note here, you might notice that we are skipping section 9 in the chapter and doing section 10. So when you go through the chapter, don't worry about section 9. I'll be talking about section 10 today, the last section, which deals with gases and chemical reaction, right? So here we're going to revisit some stuff that we did before. So you might recall, hopefully, that back in chapter 8, right, we looked at stoichiometry, right? And we did a lot of problems that involved doing this kind of work, where we went from the mass of material A to the moles of material A, and then we went to the moles of material B in our chemical reaction, and then to the mass of B. And the heart of this was these mole to mole ratios that we used to go from the moles of one thing in our reaction to moles of something else. Now we're going to revisit this idea of stoichiometry, but instead of working with masses, we're going to be working with gases. And so we'll be given not masses, but we'll be given, for example, the pressure, the volume, and the temperature of a gas in our reaction. And we will then be able to convert that into moles using our ideal gas law, where we're going to solve for our moles. And then we can use our ratio in our equation, and then we can go from moles, what we find, into whatever we're asked to. So we might be asked to find moles here. We might also be asked to find, say, the volume of some gas. And again, we can use the ideal gas law here to go from moles and combined with the pressure and the temperature that we had already to find, say, the volume of that gas. So that's the kind of stuff we're going to be doing. So this is going to be the key form of the ideal gas law that we're going to use. So let's now look at just a simple example problem here. So I'm given the problem of how many moles of ammonia are formed by the complete reaction of 2.5 liters of hydrogen at 381 Kelvin and 1.32 atmospheres. And again, we're going to assume there's more than enough nitrogen, right? So remember, so what that's really telling us here is that ammonia, not ammonia, but since they tell us there's more than enough nitrogen, it's going to tell us that hydrogen is our limiting reactant. We didn't have to actually find it like we sometimes did back in chapter 8. So we're given our balanced equation here. That 3 moles of hydrogen plus 1 mole of nitrogen gives me 2 moles of ammonia. So our first step here, if we lay out the problem right, is we know what the pressure, the volume, and the temperature of our hydrogen is. And ultimately, we want to get to moles of ammonia. But before we can do that, right, we have to get to moles of hydrogen. Then we can get to moles of ammonia. Now notice, we're not asked to go any further than that. In this particular problem, we're just doing the first 3 steps of our process. So our first step is to go from the pressure, volume, temperature into moles of hydrogen. So here we're going to use our ideal gas law, right? Our N equals PV over RT. So we're going to plug in our P, our V, and our T, making sure, of course, they're in the right units, right? So we have atmospheres, we have Kelvin, we have liters, which is what we need. So we can go ahead and use those values combined with our gas constant. Our units cancel, so we're left with moles. And so we get our answer of 0.01055 moles. Now, we should list this with two significant figures, right? Because of our volume here has two significant figures. But we're going to keep these extra digits for now. So now we've done step one. So now we're going to go from moles of hydrogen to moles of ammonia again, using that ratio. So if we look at our equation, right, our ratio between hydrogen and ammonia is we make 2 moles of ammonia for every 3 moles of hydrogen. So when we set up our ratio, of course, we're trying to find ammonia, so that's going to be on the top. Hydrogen is what we have, so that's going to be on the bottom. So plugging in our coefficients, right, we have a 2 to 3 ratio. So we apply that ratio. We take our moles of hydrogen, multiply by 2, divide by 3, and we end up with our moles of ammonia, 0.070 moles of ammonia for our final answer. So that's an example of how we can apply the ideal gas law or use the ideal gas law as part of a stoichiometry problem. At this point, I want to talk about just a couple other concepts that we have with gases. So we're going to look at something called molar volume, right? And the standard temperature and pressure for a gas. So molar volume is just as it says, right? It is the volume of 1 mole of gas. So the volume occupied by 1 mole of gas at standard temperature and pressure. So what are standard temperature and pressure? Well, standard temperature and pressure are 0 Celsius or 273 Kelvin and 1 atmosphere of pressure. So this is what we call standard temperature and pressure, or STP conditions. And so the volume occupied by 1 mole at standard temperature and pressure is known as the standard molar volume, or just molar volume, and it's always going to be equal to 22.4 liters. Now, where does this number come from? Well, if we look at our ideal gas law, right? Volume equals nRT over P. If we do this at 1 mole standard temperature and pressure, what we get is we get 1.0 mole times 0.821 liter atmosphere mole Kelvin times 273 Kelvin over 1 ATM. And so if we do this math, right, the volume will come out to 22.4 liters. Now, and one thing to always remember about the ideal gas law is that it doesn't matter what the gas is. Nowhere in any of these problems has it specified, right? We've used the ideal gas law to solve for all kinds of gases, right? Because none of these are specific to a particular gas. So the idea is that any gas, no matter what it is, under these ideal conditions, right, we're using the ideal gas law, if we have 1 mole of it at standard temperature and pressure, it will always occupy 22.4 liters. That's what we call the standard molar volume of a gas. And again, this is just to show that it doesn't matter what the gas is, right? If I have 2 gases here, helium and xenon, very different gases in terms of how big they are, their mass, etc. But 1 mole, so again, 6.022 times 10 to the 23rd molecules, right, or atoms of these gases, so same number of atoms, will occupy the same volume. Now, of course, one thing that will be very different, right, we say they're identical, and they are identical in the sense that they will occupy the same volume, but they are still quite different in terms of their mass, right? These are different mass molecules. So while we have the same number, just like we talked about why different atoms have different molar masses, because the individual atoms or molecules are different masses, these samples will be identical in a lot of ways, but they will have very different masses because of the masses of the individual atoms. Okay, so now let's look at a simple problem dealing with how we might use the standard molar volume in a simple stoichiometry problem. So if we look at this problem, we want to calculate the number of liters of a gas that form at STP, or standard temperature and pressure, when 0.879 moles of calcium carbonate undergo the reaction given here. So we have calcium carbonate, 1 mole, yields 1 mole of calcium oxide plus 1 mole of carbon dioxide gas. And in the problem wants to know how many liters of gas. So now what we're finding here is the liters of carbon dioxide, that's the gas. Then we start with 0.879 moles of calcium carbonate. So this is a simplified stoichiometry problem, right? We don't have to convert into moles of calcium carbonate, right? We're already given that, and we want to go to moles of CO2. So again, we're going from moles of one thing to moles of something else. So we're going to use our mole-to-mole ratio. So in this case, our mole-to-mole ratio is 1 to 1. And then once we know moles of CO2, ultimately we want to know the volume. Now, we'll talk about this in a second, but in the previous example, right, I said that you could use the ideal gas law to do that, right? You could use the ideal gas law to find this volume using our temperature and pressure, right, that we're given, right? We're at standard temperature and pressure, right? And we could use the moles of CO2, right? And we could find volume. But we can have a simplified way to do that, and I'll talk about that in a second. So let's do the first step, where we simply take our moles of calcium carbonate, and we use our 1 to 1 ratio here, and it's going to give us our moles of CO2. Now, the math isn't very difficult here, of course, so we're going to end up here with 879 moles of CO2. Now, this 22.4, the standard molar volume here, right? So this is the standard molar volume, gives us a shortcut, right? So anytime we're at STP conditions, we can use this volume to represent the volume of 1 mole of gas. So if 22.4 is the volume of 1 mole, then we can use that value to figure out the volume of any number. So for example, half a mole would be 11.2, right? Or 2 moles would be 44.8. So we have 0.879 moles, and we want to figure out how many that's going to be. So we're going to simply take this times our 22.4 liters per mole, and that's where we're going to get 19.7 liters of carbon dioxide, or 87.9% of that 22.4, right? Because we have 0.879 moles. So it just allows us a little bit shortcut way to get to this value without going through the whole ideal gas law. But remember, this can only be used if you're at standard temperature and pressure conditions, right? Only STP conditions can we use this 22.4. Now, you could test this if you go ahead and plug this moles in for N and then plug your standard temperature and pressure, here you have 1 atmosphere, 273 Kelvin into there, you should get the same volume as we got here. Just a little simpler calculation. So that ends what I want to talk about for this. I'm going to close here by doing an example problem. It will be our last thing that we do here. Okay, so I want to close by doing one final example problem here of stoichiometry of the gas. So we're given a reaction here. We have 2 moles of silver oxide, solid, reacts to give 4 moles of solid silver and 1 mole of oxygen gas. And so what we're told is if we're given 4.58 liters of O2 is formed at 745 millimeters of mercury and 308 Kelvin, how many grams, right, of this silver oxide solid are reacted? So in other words, they're asking us how much of this do we need to give 4.858 liters of oxygen gas, given our 2-to-1 ratio here. So if we draw out sort of our plan here, we're given the gas conditions, right? We're given volume, we're given pressure, and we're given temperature, right? So we're given PVT of O2, and we can then use that to get to moles of O2. And then, of course, once we get that, we can do our stoichiometry and get to moles of silver oxide. And then eventually, because what we do is we can get to grams of silver oxide. So let's start out with our step 1 here, right? So we're given pressure, volume, and temperature. We want to go to moles. So that's going to be an ideal gas law, right? We're going to use PV equals nRT to do our problem here. So start out with our version of the ideal gas law, and I'm just going to go ahead and start with the one that we have N by itself, so PV over RT. So if we plug in the values that we have, so we have, let's go over here and see what we're given. So we have a P of 745 millimeters of mercury. We have a V of 4.58 liters. And we have a T of 308 Kelvin. Now, one of the things we have to be really careful of here is, remember, because of R, right? R equals 0.0821 liter atmosphere mole Kelvin, we have to have certain units, remember. So one of the units that we have to have is, we know that our pressure has to be in atmospheres, but we have it in millimeters of mercury. So we're going to have to change this to atmospheres before we solve our problem. Now volume is in liters, temperature is in Kelvin, so we're good there. So let's do this conversion. So how do we convert from millimeters of mercury to atmospheres? So the key conversion here is, remember that 760 millimeters of mercury equals 1 ATM. So if I have 745 millimeters of mercury times 1 ATM over 760 millimeters of mercury, I can do my conversion, and that tells me that I have 0.980 atm as my pressure. So now that I can have the right units, I can go back and plug it in here. So I have 0.980 atm. I have 4.58 liters. I have 0.0821 liter atmosphere mole Kelvin. And I have 308 Kelvin. So if we cross our units, right, atmospheres cancel here, liters cancel here, kelvins cancel here, we're going to be left with moles. So if I do my math, I get that N is equal to 0.1775 moles of O2. Now, of course, eventually, right, we're going to round that or stop that at 3 significant figures, but we're going to carry an extra one along with us here. Now, so we've done the first step. So now we need to do our second step, right? Go from moles of oxygen to moles of silver oxide. So we go back to our balanced equation, and we see that our relationship, right, is for every 2 moles of silver oxide, we make 1 mole of O2. So if I apply that ratio, right, where I have O2 on the bottom, silver oxide on the top, we have 2 mole here, 1 mole here. And so we end up with moles of O2 canceling, and we end up with 0.355 moles of silver oxide. Now, our last step, right? So now I have moles. So I did step 2 here. So now I'm going to do step 3, the last step, and I'm going to take the moles here and convert it into grams. And so remember, to do that, I need the molar mass, right? So here, to do this step here, I'm going to need the molar mass of silver oxide. And so if we calculate that, the molar mass equals the mass of 2 silvers plus the mass of 1 oxygen, which should give us 231.74 grams per mole silver oxide. So then we're going to do our conversion. So we have 0.355 moles of silver oxide times 231.74 grams per 1 mole and so we're going to end up here, my moles cancel, and we end up with 82.6 0.3 grams of silver oxide at the end. So we had a three-step process here. So just like our stoichiometry problems that we did back in chapter 8, but instead of starting with a mass and going to moles, and then going to moles of what we're trying to find, and then going to a mass, we started with the gas properties because we were dealing with a gas, and we used the ideal gas law here to do our first step to find moles. So it provides a different way to get to moles of a gas if we know the pressure, volume, and temperature. So in a follow-up video after this, I will do a few more sample problems just to give you some more examples to look at. So look for that video to come right after this one.